This is a continuation on lecture for IE 3340, Operation Research. This lecture, again, is a continuation on the integer programming topic. In the first part of this video, we would discuss the differences between linear programming models and integer programming models. And the major idea in terms of the differences is that for one of them, we are not limiting our decisions to be integer, whereas for integer programming models, we are forcing our decisions to be integer values. Those could be integer values that go from 0 to any number, or could be decisions that are binary. In both cases, we are dealing with integer solutions. So we went through the formulation of different applications in integer programming. And we also discussed that solving integer programming models is challenging. We discussed that we cannot apply the simplex method because since the feasible region is no longer the same, feasible region is now restricted to be integer values, the simplex algorithm will not work for integer programming models. So in this lecture, we are going to discuss an algorithm that is used to solve integer programming models. The algorithm name is the branch and bound algorithm. And we're going to explain the steps for the algorithm and also how do you know when to have when to stop in order to know that you have obtained an optimal solution. So in terms of solution methods, integer variables make an optimization problem difficult to solve. Memory and solution time may rise exponentially as you add more integer variables. And this in terms of computational time. So if you run a problem that is, if you try to solve this problem using a commercially available software that has the implementation of the branch and bound algorithm, then it will take more time as you increase the number of decision variables. Even with highly sophisticated algorithms and modern supercomputers, there are models of just a few hundred integer variables that have never been solved to optimality, meaning that the number of iterations that you have to do is so big that you will not be able to get a solution, let's say in years. This is because many combinations of specific integer values for the variables must be tested. Each combination requires the solution of a linear or nonlinear optimization problem. So every time that you do a step in the algorithm for the branch and bound, every time you search for an integer solution, you have to solve a linear or nonlinear optimization problem. So think about solving 1,000 linear programmings as you search for an integer solution for your problem. The number of combinations can rise exponentially with the size of the problem. So there are different solution methods for integer programming models. You have the branch and bound algorithm, which yield the optimal solution and is more efficient than enumeration. Enumeration will also yield the optimal solution, but it's more time consuming. Enumeration, basically what it means is that you are going to take every possible combination that is feasible for your problem, every possible decision variable combination, and you're going to test them all. And then after you test them all, you are going to look for the one that is optimal. So you are maximizing, you're going to select the one that is maximizing your objective function. If you're minimizing, you're going to select the one that is minimizing your objective function. So total enumeration is an option, but it will be very time consuming. So in branch and bound, we'll also yield the optimal solution and we'll cut some of the steps that you would do for total enumeration. Usually, integer programs are solved by some version of the branch and bound procedure. Branch and bound methods implicitly enumerate all possible solutions to NIP or integer programming. By solving a single subproblem, many possible solutions may be eliminated from consideration. Let's look at this example in which we are going to implement the branch and bound method. So the example, you have Telfa Corporation manufactures tables and chairs. We have for each tables and chairs, the amount of labor in terms of hours that is needed, the square board feet of wood in terms of material that is needed for both tables and chairs, and the profit that you make by selling each one of these items. Currently, 6 hours of labor and 45 square board feet are available. So we will formulate and solve an IP to maximize the Telfa's profit. So these are our decision variables. We have X1 is the number of tables manufactured, X2 is the number of chairs manufactured. Our objective function is to maximize these profit that you make by selling X1 tables and X2 chairs. And then we have a constraint for the labor. We don't want the labor to be more than 6 hours, which is what we have available. And we don't want to go above the amount of material that we have available, which is 45 square board feet. And we want our decision variables to be positive and also integer. So the first step of the branch and bound method is to solve the LP relaxation of the IP. So we are basically going to ignore the restriction of having integer solutions. So we're going to solve it as if this were a linear programming model. So using the LP relaxation and using the graphical method, since this is a 2-decision variable problem, we can apply the graphical method, which you're familiar with. We draw all the constraints for this problem. So we have 9x1 plus 5x2 equals 45, this constraint. And then we have the second constraint, x1 plus x2 equals 6. So using that information, we can show the feasible region, which is the shaded area, and drawing the isoprofit line, which is this dotted line right here. We can move that isoprofit line in this direction in order to find the optimal solution. So that isoprofit line will be moved parallel to it until we touch the last point of the feasible region, which is this point right here. And that is the optimal solution. And as you can see, this has a solution which is a fractional. Both of them are fractional solutions, which is what we are illustrating here. So x1 is a fraction, 15/4, and x2 is also a fraction, 9/4. So as a rule, we always know that the optimal value for the integer program is less than or equal than the optimal value for the LP relaxation. Okay, so we know from here and from this rule that the solution that we just obtained is going to be always, because this is the solution for the linear program, is always greater or equal to the solution that you will obtain for the integer program. So our solution in terms of the objective function, z, when we find the optimal solution for the integer programming, will be less than 165/4. Less than or equal to. It will never be greater than that. This implies that the optimal value for the IP cannot exceed 165/4. The optimal value of the LP relaxation is an upper bound for the profit. Okay, so we know that the solution, the integer program solution will not exceed this 165/4 profit. So our solution is going to be bound. That's what we call the LP relaxation solution and upper bound for the Telfas profit. So now we move to step 2, which is the partition the feasible region for the LP relaxation in an attempt to find out more about the location of the integer program optimal solution. So you're going to choose arbitrarily a variable that is fractional in the optimal solution for the LP relaxation. So arbitrarily we select x1. x1 equals 15/4. Observe that every point in the feasible region for the IP must be either x1 less than or equal to 3 or x1 greater or equal to 4. So that's why by looking at this is about 3 and 3/4, right? So the closer integer solutions for this value are 3 and 4. So that's why observe that every point in the feasible region for the IP must have or has to be less than or equal to 3 or greater or equal to 4. So that's where we are going to partition, right? The feasible region for this problem. With this in mind, we branch on the variable x1 and create the following subproblems. Subproblem number 2 is going to look at the original feasible region, and we are going to add a constraint x1 greater or equal to 4. Again, our goal is to find for an integer solution. So that's why we are partitioning the feasible region. We want partition the feasible region because we're searching for that integer value. Closest integer values to our current solution for x1 are 3 and 4. So we are adding these two constraints, and we're creating two new subproblems. Subproblem 2, which is adding the constraint x1 greater or equal to 4, and subproblem number 3, which is adding the constraint x1 less than or equal to 3. If we look at the feasible region now by adding those two constraints, basically what we are doing is the following. We are adding this constraint and this constraint. So this one, this constraint is x1 greater or equal to 4, and this constraint is x1 less than or equal to 3. So now we create subproblem 3 and subproblem number 2. We have two separate feasible regions now. So because subproblem 3 and 2 and 3 were created by adding constraints involving x1, we say that subproblem 2 and 3 were created by branching on x1. And that's where the name of the algorithm is derived from. So we are branching, branch and bound. So we branch and then we bound, and then we continue until we find the optimal solution. So we have two feasible regions now, A, B, C for subproblem 2, D, A, D, E, F, G for subproblem number 3. So step 3 is to choose any subproblem that has not yet been solved as an linear program. So we are going to choose subproblem number 2. So subproblem number 2 is this one, this triangle right here. So we are choosing subproblem number 2. So we are going to focus on this triangle. And if we use the isoprofit line, so if we use this isoprofit line to determine the optimal solution for this subproblem, if you move that in this direction, if you move this line in this direction, the last point that is going to be touched by the isoprofit line is going to be this point C. So the optimal solution to subproblem number 2 is z equals 41 with x1 equals 4 and x2 equals 9/5. Okay, so what you see now is that we were able to find one of the coordinates for this problem, or one of the decision variables is now integer, but we're still facing an issue here with 9/5. So after branching, we have solved subproblem number 2, and this is the solution. Z equals 41, x1 equals 4, and x2 9/5. The optimal solution for subproblem number 2 did not yield all integer solution, so we choose to use subproblem number 2 to create 2 new subproblems. Choose a variable that is fractional in the optimal solution for subproblem number 2. The only decision variable that is fractional is x2 equals 9/5. So we are going to branch on 9/5. We are going to partition the region for subproblem number 2 into those points having x2 greater or equal to 2 and x2 less than or equal to 5. So again, same principle. So what are the 2 integer values that are closer to this value? 1 and 2. So we are going to add those constraints to our subproblem. X2 less than or equal to 1 and x2 greater or equal to 2, which will create 2 new subproblems. Subproblem number 4 is taking subproblem 1 plus constraint x1 greater or equal to 4, and now we are adding x2 greater or equal to 2. So this is going to be equal to subproblem number 2 plus constraint x2 greater or equal to 2. Subproblem number 5 is taking subproblem 1 plus constraint x1 greater or equal to 4 and x2 less than or equal to 1, which is equal to the subproblem 2 plus constraint x2 less than or equal to 1. So if we perform that, now we are looking at x2. So the constraints are going to be in this direction. This one is x2 greater or equal to 2. And this one is x2 less than or equal to 1. Okay, so if you look at this, the feasible region for this new subproblem, that feasible region is outside the original feasible region for subproblem number 2. So anything else above that line is infeasible because it's not part of the feasible region. So we can focus then on x2 less than or equal to 1, which is still cutting part of the feasible region and is making this problem a little smaller. So what we find out now, let's see. Remember, this is your isoprofit line. So we use the isoprofit line to find the optimal solution now for subproblem 5. So the set of unsolved problems consists of subproblem 3, 4, and 5 at this point. This is subproblem 4. At the top, subproblem 5 is at the bottom, and subproblem 3 is the one that we haven't discussed yet. We'll get to that one in a minute. So having this issues, any subproblem that has not yet been solved as a linear program. So if we look at subproblem 4, as I mentioned already, is infeasible. So we can state that in our branch, in our 3. So that's what we are saying here. If we add that constraint x2 greater or equal to 2, the problem is infeasible because it's not touching the feasible region. That new constraint is basically limiting our solution space to that area above the x2 equals 2 line which is not touching the feasible region. So that's why this subproblem 4 is infeasible. For subproblem 5, as I mentioned, we are touching the feasible region. We are constraining the feasible region. So we can look at, and what we did right here is that since this cannot yield an optimal solution, we phantom that node. Okay, so we are not going to branch anymore in that branch. For subproblem 5, choose any subproblem that yet has not been solved. So we choose subproblem 5, and using this isoprofit line, moving in this direction, we know that the last point is going to be touched, that is feasible, is that point. So the optimal solution now to subproblem 5 is z equals 365 over 9, x1 equals 40 over 9, x2 equals 1. The optimal solution to subproblem 5 did not yield all integer solution, so we choose to use subproblem 5 to create 2 new subproblems. So we choose a variable that is fractional in the optimal solution to subproblem 5, x1 equals 40, and branch. Partition the feasible region for subproblem 5 into those points having x1, because these are the integers that are closer to this, so 4 and 5. So x1 greater or equal to 5 and x1 less than or equal to 4, which creates 2 new subproblems. So problem 5 plus constraint x1 greater or equal to 5. So problem 5 plus constraint x1 less than or equal to 4. So this is the solution for the previous slide. We notice that x1 has a fractional value, so we are partitioning the feasible region into 2 new subproblems, and we are branching for x1. So you have to pay attention. Your branching is happening for different decision variables, so you need to keep track of that. So in this case, we are branching for x1, and we are creating 2 new subproblems. The set of unsolved problems at this point are subproblem 3, which we are going to discuss in a minute, subproblem 6, and subproblem 7. So now we are adding these 2 constraints to that feasible region. So this is x1 less than or equal to 4, and this one is x1 greater or equal to 5. Okay, and this right here, that line, this blue line is the feasible region. So as you can see now, our feasible region for we choose any subproblem that has not yet been solved as an LP. So at this point, we are solving subproblem 7. Subproblem 7 is basically limiting, with that additional constraint, is limiting our feasible region to be just this line. Okay, so we are going to solve that problem by using our isoprofit line. So if we move this isoprofit line in parallel to it, the last point that is going to be touched in that yellow line is going to be that point. And as you can see, that point is providing us with a optimal solution that is integer for both of them, x1 equals 4, x2 equals 1. So we are updating our tree, and you can see now we have found a candidate solution that is integer. So a candidate solution is a solution obtained in which all variables have integer values. Okay, so this is a lower bound for the original integer program. The set of unsolved subproblems now consists of subproblems 3 and 6. So We still have this problem that is not solved and this problem that is not solved. Okay, so we are going to look at choose any subproblem that has not yet been solved. So we choose subproblem 6. Subproblem 6, remember, is looking at this constraint greater or equal to 5. And if we look at the feasible region, when you add that constraint, the feasible region is just going to be that point. Okay, so our feasible region now is limited to a single point. So obviously, if we use this isopropyl line, and we are just focusing on that point, that's going to be our optimal solution. So the optimal solution to subproblem 6 is z equals 40, x1 equals 5, x2 equals 0. So the solution obtained in which all variables have integer values is that point, 5 and 0, and is giving us a optimal solution for the objective function equal to 40. So if we go to our tree now, you can see that this is the new solution. And you can compare the objective function value of these two, and you say, okay, we are maximizing, this is better. So the solution that we just found is better than this one. So that means that this solution can be phantom. Okay, so we have a new candidate solution. We still have one problem that has not been solved. Choose any problem that has not yet been solved. That's a linear program. So problem number 3. So problem number 3 is looking at this area that we have not discussed yet. All the steps that we just made was looking at this triangle. But in this problem, I mean, again, using that isopropyl line, you move that parallel to it, the last point that you're going to touch is this one. And it shows up as an integer solution. So the optimal solution to subproblem 3 is z equals 39, x1 equals 3, x2 equals 3 as well. So that's an integer solution. However, that solution is not better than the one that we just found, which is z equals 40. So by adding this solution, z equals 39, this one's still better. So we can phantom that one. And then the optimal solution for our problem is z equals 40, which means that we manufacture 5 tables in 0 shares. And that concludes our explanation of the branch and bound method. In the next video, I'm going to discuss an additional problem. But in terms of this lecture, we discussed the introduction on what integer programming is. We discussed different integer programming types. We formulated integer programming problems. And then finally, in this video lecture, we discussed the branch and bound method to solve integer programming models.